Good afternoon. I'm Kathy Chute, the Executive Director of the Institute for Applied Computational Science here at Harvard, and I'm delighted to welcome today's seminar speaker, Mark Michalski. He's coming from not too far from Mass General and the Brigham's Special Center for Clinical Data Science, and I think he's got a great topic. As most of you know we have two more sessions, two more seminars in this series, and we'll work up again in the spring. The next ones are November 9th. With Flavio Camon, who's from here, speaking, and also the week after that, actually 3 weeks after that, and November 30th, is Julia Ling from Centrine Informatics. So I hope you'll join us for those as well. So Mark this is an MD, doctor, but really doing amazing work and leading an amazing organization in machine learning. What the organization does, it applies and translates novel machine learning techniques into clinical practice. And Mark has a background in medical software and devices, as well as having done his residency and gotten a medical degree from Stanford quite a few years ago. He's a radiologist originally by training, but really has had a sort of a broad career across both industry and academia and medicine. And he's going to take us through machine learning and the healthcare enterprise. Thank you, Mark.
Thank you. Thanks very much. Thanks for having me. Thank you. So thanks very much to the seminar organizers for having me. I really appreciate it. It's really great to be over here. And to tell you a little bit about how we're starting to consume some of the great science that you're doing here in the healthcare practice. I'll start out with a little bit of a story. Does anyone know what the match is? The match? Quite a few of you. Okay, I was recently having a nice bottle of wine with a friend of mine, and this was a friend who was in radiology as well. And we were talking a little bit about how machine learning is starting to transform our field. And he said to me, you know, Mark, I really appreciate the work that you guys are doing and the impact that machine learning is going to have on our field. You know, I understand it. But, you know, Mark, I just don't believe that clinicians, radiologists, diagnosticians will really ever truly accept this technology because MDs, they're just so, you know, bullheaded. They're so strong-minded. And it's going to be really hard to get them to trust a computer with anything of real import in their lives. And so as happens, you often have the best come back a couple days later, and I did, which was match day. So match day is basically the day when every MD student in the country submits a rank order list of all the places that they want to go to residency. And the residencies rank order them, and it goes into a giant computer in Chicago and outspits your future. So match day is kind of this thing where you basically find out exactly where you're going to go. And when you go to match day, you find out essentially, are you going to be a surgeon? You're going to be a radiologist, and where are you going to do those things? And you know, not that long ago, we were having this conversation, and I thought back to my time in medical school. And I thought about one of my roommates in the very first year of medical school, which is, was a guy who really wanted to be a surgeon. And you know, the funny thing is we have a term for these type of people. I see actually one of my colleagues back there who is a surgeon, so please don't feel offended. But there are some people in their first year, they know they're going to be a surgeon. They're probably born to be surgeons. And we call them the gunners, because they know that they're going to be the top in the anatomy class, the top in the physiology class. And you know these people not only because they really are dedicated to the craft, but no matter where they are, they're wearing scrubs. So they're either at the bar, they're wearing scrubs. And so I had a roommate like this. I was very fortunate to have a roommate like this because he was much better at anatomy than I was, much better at just about every subject, is constantly studying in his scrubs. And as it happens, over time, we just lost touch with one another. But I saw him recently at Exponential Medicine, which is kind of like a TED Talk sort of thing. And I was giving a talk there, and I ran into him, and he wasn't wearing his scrubs anymore, but he kind of looked like this guy. He kind of like had all the like quantified self accoutrement like all over himself, and like had like little things like beeping and stuff. And So I asked him, it's like, so how's your surgical practice going, dude? And he said, you know, I'm not doing surgery anymore. I was like, you don't do surgery, that's who you were. And he said, no, man, now I do AI. Mind-blowing. And so, you know, part of the reason, you know, I give this talk is to get people set on, like, why are we where we are? And I mean, for this audience, you know, I think this is all pretty much, you know, why we're where we are. But you know, 2012 was a big moment in the computer vision community. This is when AlexNet essentially blew away the competition, and every year since, it's just been different. And that was the beginning of deep learning. 2012 is sort of when it really started to take off. And you know, after ImageNet, you know, we in the radiology community and the pathology community and diagnostics and medicine, we didn't know that any of this was happening until a couple of years later. It was really when we started to see headlines like this in the popular press, like, you know, obviously big acquisitions, like DeepMind, but we, in the medical field, started to see this kind of stuff too, which was big acquisitions for data. And for example, Merge was a PACS system. That's the kind of system that you use to look at images, to store images, and got acquired for $1 billion by IBM. And a lot of people were scratching their head, why was that happening? And I think the people in this room kind of know why, because data is pretty key here. That was 2014. And then we started to see market research firms start kicking these sorts of things out, like in 2015, finding out that, man, there's a real big market here. And I think 2016 is when this slide is from. So 2016, CB Insights published this thing. This is a slide that gets passed around to everyone in the healthcare world who's working in machine learning. It's 106 startups transforming healthcare and artificial intelligence. And you know what? You know, now I'd venture a guess that there's 106 startups transforming healthcare or AI just in Boston alone. And by the time we're done with this talk, there'll be another one. Another one will have probably gone away. So, you know, probably a couple of you guys know the people in those startups. You know, this is when actually real conversations started to happen. 2016 is kind of when we in the healthcare field space, we in the diagnostic world started to recognize that there was actually something happening. And we started to see these kinds of publications. Many of you are probably familiar with this. This was, I think, 2017. Sebastian Thrun's lab did this classification task, which was essentially took classified nevi moles and tried to predict the likelihood of them progressing to melanoma. It pre-trained on a bunch of data from the internet, used seven dermatologists to do classification on the images that were collected at Stanford, and I think this was Inception v3. And you know, the two things that really came out of this that were kind of interesting were, one, we got near human performance, and two, you know, it was with what some people might say is a commodity model. You know, it was Inception. This is an interesting one out of the University of Adelaide that came a couple months later in the field of radiology. And this one is really about kind of data exhaust. So Luke Oden-Rader, a PhD student who's also a radiologist, thought it might be interesting to see if we can identify features on chest CTs that would essentially be a prognostic marker, no matter what your diagnosis is. So he took CTs, chest CTs, non-contrast, after the age of 65, identified 7 features in those images. I think it was emphysema at the bases, big left ventricle, calcification in the aorta, these sorts of things, which are kind of related to aging. And by identifying these features, actually created this beautiful Kaplan-Meier curve. So no matter what your diagnosis was, no matter what you got the CT for, you have this pretty nice prognostic marker. And we'll talk a little bit more about that here. Actually, it turns out by doing this, you can do all sorts of, this kind of approach really is powerful for a lot of different things in medicine. Finally, some work that's from friends nearby at the Martinez Center. This is Matt Rosen's work and Bo Zhu, applying machine learning in the scanners themselves. So this is something that I'll talk about a little bit later, but essentially using deep nets to do the essentially the inverse Fourier transform on case space. So essentially doing reconstructions faster with sparser sampling. This one is more recent. I think this was earlier this year. This was University of Chicago and UCSF with Google Brain. The topic here was essentially to do a lot of risk labeling. So a big problem in healthcare is trying to predict who's likely to get better and who's likely not to. What's the likelihood of people coming back to the hospital after they've been discharged? And that's a really, really important thing for healthcare costs. So this was published back in, I don't know, like I think it was March, April or so, and benchmarked essentially neural networks versus largely logistic regression, so like the standard models. And so this one sparked a little bit of debate. So the performance here with neural networks is better, but there's a lot of debate about whether this actually added a lot of value. So we may be starting to see, partly because with a standard statistical model, it's very clear why things, what the drivers of your model are. With neural networks, sometimes it's a little bit more difficult. So we'll talk a little bit more about that. So I just gave you sort of a bunch of different articles that started coming out in like the 2016, 2017 timeframe. And the reason for this talk is essentially to tell you how, in healthcare, how we're consuming some of this technology. So as I said, 2016, we kind of became aware of what was going on. And 2017 is when things started hitting full steam. 2018 now, everything's on fire. Everyone's talking about machine learning with respect to, especially diagnostics, but almost everywhere in healthcare. Now, the ingredients for machine learning these days, it's like computational resources, data, and algorithms. But the reality is, another way to sort of position this is, well, GPUs, I think, is largely democratized. So if you have access to the cloud, which we all do, then you can get access to GPUs and training, compute needed for training. The algorithms, on the other side, is really about talent. So all of you know how to get access to these algorithms, how to do the parameterization, how to actually make these models, to optimize these models. And a lot of this is increasingly getting easier and easier. But the thing in the center is oftentimes hard to get, right? And so even if you have access to it, it's oftentimes data is dirty. It's hard to clean, to put it in the places where you need it to be to actually do the model training is really difficult. And so when you think about where a healthcare system can help, well, it's oftentimes in data, right? It was sometime around 2016 when some of the leadership at Partners Healthcare started to ask this question, what do we have to do to actually contribute to this space? Recognize that algorithms and GPUs we didn't really have access to, or talent and the appropriate talent in the GPUs we didn't have access to, but we do have all this data, and it turns out Partners does have a lot of data. So I'm a radiologist. I tend to focus on the diagnostic side, but Partners covers a lot of lives and generates a lot of data, and probably pretty critically, it made some pretty good investments early on to collect this data in a format that was relatively clean. We have sources like the RPDR, we have the biobank at Mass General, and so there are a lot of resources really at Partners in terms of data. Though I will say it's in a lot of different silos. So lots of, just like every major academic medical center, major healthcare provider network, this data is really in lots of different places. It's hard to get access to sometimes, but if you can tap it, it can be quite valuable. And so partly because of this and a recognition that there was value in this data, the center was created. So the Center for Clinical Data Science was one of partners' reactions to all the science, or what was happening in machine learning. And this all kicked off in July of 2016, so we're a little over 2 years old. And the focus of the enterprise is a little bit different than most academic sort of research enterprises. So we're very product focused. So the mandate that I was given, this all started in the Department of Radiology at Mass General, but it's expanded a lot. But the initial mandate was really something special is happening in machine learning. We're seeing some pretty transformative technology for diagnostics. Is it real? And if it's real, how can we contribute? And how can we incorporate it within our own practices? Another way of looking at this is because we're in such a great ecosystem with smart people like all of you who are building this technology and doing the basic research, is there something that we can do to help with the development of some of the tools, helping with the translation? And ultimately, when it comes down to it, Mass General and Brigham are full of homegrown technical solutions, lots of software that's been built from the ground up. But oftentimes what happens is once you've created those solutions, then someone leaves, and ultimately things change. And so you need to find a way to do the service and support on all this technology, right? So you have to find a way to actually turn it into a product and commercialize it and have support for that technology. So I'll just tell you a little bit so that how we've grown. This is a little bit of how we've grown. So right now we're at about 30, 35 people altogether. We're kind of equal parts ops and product, data science and data engineering, and software development. So I'll just tell you a little bit about what we've learned in the last 2 years or so. So the first thing that we've learned is that this is probably no surprise to all of you. It really is all about the data and getting access to that data and making the data clean. It's really data engineering tasks are central to what we do. So we started by hiring a lot of data scientists, but ultimately it was tooling that allowed us to move fast. Each one of these boxes here represents some tool, whether it's a pretty complex tool or something pretty simple. Actually, one of these viewers was, the Sake viewer was a collaboration with some of the IACS students in our first year, which is pretty cool. So we've got a bunch of tools that we had to create, both for visualization and cleaning and lots of other stuff. Even to get off the ground, you can do models, you can find annotated data, but to make it scalable within a healthcare enterprise takes a lot of tooling and a lot of data pipelining. So just give you an example of the central challenge when it comes to building these models. It's about cohort creation, cohort creation, cohort creation. You guys know what I'm talking about? Is this familiar to you? So it's really about first selecting who the appropriate patients are and who the appropriate negatives are. And you would think that's pretty simple, right? So, okay, so I want to create a model for pancreatic cancer, right? And let's say I want to be able to do a segmentation task on pancreas cancer, or like pancreatic mets or something like that. You think it's simple to find all the pancreatic patients, but actually it's pretty complex. The billing code data sometimes is not exactly what you're looking for. You have to look through clinical reports, but oftentimes we still have problems with negation with all the technology we have. And ultimately, it almost always comes down to some sort of manual process of looking through the reports to figure out whether this person has this diagnosis or doesn't, or has the features that you need to actually perform the task. So we might start with tens of millions of reports, whether those are clinical reports or even pathology or radiology reports. You have to go through some process of funneling with exam code or billing code data to end up with these curated reports. But even then, you need to go through the process of starting to label some of these reports. In other words, the reports themselves, even if you perform a regular expression or NLP task on it, oftentimes you still need a manual task. There's a manual process to do the quality checking. So we created this tool which it features some regular expression, but ultimately you need someone to go through the process of doing this labeling. So that's part of our world. So that was the first thing to learn. The second thing we learned is that it wasn't enough for us to justify our work and to justify our existence. We really had to do a lot of work to integrate these solutions. So again, not enough to be able to make models. First, you need to be able to deal with the data. And then you need to be able to take that model and integrate it into the healthcare enterprise. And that oftentimes is a real challenge. So to do this, we had to create a couple things. One, we had to create an alpha testing environment. So for radiology, for example, we got a workstation. We actually got representative workstations of each one of the hospitals in our enterprise. And then we had to sort of start to understand how we could hack some of these things without breaking the workflow. I'll give you an example, but a lot of the systems in the healthcare enterprise don't have standard APIs. And so you have to find other ways to get around some of those systems to take advantage of the opportunity. The other thing is ultimately you have to integrate this within a workflow that's clinically relevant for you to do the validation. So this was one of the things that we built first. We created a pipeline which took images from the PACS system. And just so I can pull the audience, when I'm talking about the PACS, do people know what the PACS system is? How many people are working in diagnostic imaging or diagnostics in healthcare? Okay. How about image classification tasks? Yeah. Okay. So the PACS system is where the medical images live. And then we typically run it through a process called CTP, which is a set of tools, set of libraries really, that can strip some of the PHI, some of the personal health information to anonymize the images. And then you'll run it through, essentially we have a standard Docker container which has a couple of the key tools within the Docker container that will allow you to essentially swap out whatever kind of algorithm you want, and then you can get the feedback that you need to improve upon that model. So this is tooling that was required to make this all happen. So these are kind of challenging steps. The good news is that once you get some of this out of the way and you place this investment in a healthcare system, there is a lot that you can do. And it's almost boundless. The number of emails that we get, and sort of questions, clinical research questions, opportunities to really move the needle when it comes to healthcare practice is really phenomenal. It's really boundless. So this is a good representation of that. We've got about 40 projects underway. We only do internally maybe half, probably less. And the rest is just helping them get access to data, helping them access to cohorts, helping with annotation tasks. So making the tooling available for them to do annotation, and ultimately, hopefully, getting these solutions into the reading room. So I'll give you a couple of examples of that now. So one of the first things we kicked off was work and stroke. So many of us have been impacted by stroke in our lives, probably someone that we love. And I think this is one of those opportune fields where a lot is changing really fast. So part of the reason for that is a New England Journal article that came out about a year ago called the Dawn Trial. Does anyone know what I'm talking about with the Dawn Trial? Let's see if anyone does. Okay, no one. So maybe one person. So this is actually hugely impactful. With stroke, unfortunately, it's an infarction. It's basically a clot that kills brain tissue. And the problem is that there's not always a lot of good collateral flow in the brain. That means there's not a lot of backup for the blood supply. So that's why stroke happens. You get a clot, and essentially that brain infarcts or loses blood supply and dies. And so for a long time, really we thought there was very little that you could do after a certain amount of time. So after about 6 hours, we thought that brain was just dead. and there's not a whole lot that you could do. And not very many people make it to the hospital in time to be treated. So that's a real problem. And so for many, many years, for really the majority of the majority of our history, right? We haven't been able to do very much. We can sometimes inject a clot buster. If we get them at exactly the right time, we can put a catheter up into the head and through the vessels and squirt a little bit of clot buster and maybe help. But there wasn't a whole lot we could do until recently. We found out that actually you can treat strokes almost probably up to 24 hours or more. And that changes everything, because if you can treat someone up to 24 hours with intravascular therapies, which is how you would do it now, it's basically bring a catheter up into the head and intervene that way. There's a tremendous amount that you can do. This changes a lot, and so everything is kind of moving now. Workflows are moving, the way that we're going to triage patients are working, the way that we interact with the hub hospitals. So places like Mass General and Brigham are kind of these hub hospitals, and there's spokes, these spoke hospitals in the community. Getting patients in faster, because there's something we can do, has actually opened up this field. And it just so happens that, that this is happening at the same time that machine learning is really taking off in the diagnostic space. So we decided that this would be a good opportunity to start building models related to stroke care. So I'll give you the first example that we set off on. This is a DWI image, MRI image type of sequence that's specific and sensitive to stroke. So this big bright spot here, that's all stroke. And what you might be able to see is that there's this golden line around that big bright spot. Well, that's I think that's our segmentation algorithm, and this was, I think, trained on about 10,000 images. So you see that there's a pretty high fidelity, there's high concordance, but we learned a couple things in the process here. We learned some of the bad and some of the good. So if you look at this, first of all, many of you might say, well, the SNR is really good for the image. So there's a big bright spot, in other words. So do we even need this tool? Do we even need a segmentation tool here? And the answer is, well, first of all, it's harder than we thought. And the answer is still very much yes. So why is it harder? Well, it turns out that every scanner, especially MRIs, have a high degree of variance when it comes to their acquisition parameters. So not every DWI image looked like this, and the segmentation algorithm was particularly sensitive to differences in the acquisition parameters and the scanner types. That was why it was harder. But one of the things that we found out, and this is a common thread, this is a common theme in our experience, is that while we did this, when we did this algorithm, we actually found out that this was useful for a lot of folks. For example, there's someone who is trying to create a method for predicting the prognosis of a patient after stroke. And it turns out that if you overlap the area of infarction with an atlas that will tell you where the cortical white matter tracts are, that's kind of the wiring in your brain. If it wipes out the wiring, then you're less likely to recover. So that concordance, that overlap, is an important metric for prognosis. And that's an important thing for planning. For anyone who's experienced this, in their family or personally, knowing what's going to happen in the next couple days is really, really important. And that's important for patient care, but it's also important for peace of mind. So this is one model of about 7 that we're working on in the stroke world. Moving on a little bit, so here's another example of something we're building. It's a tool for MRIs of the lumbar spine. That's your back. So when you have sciatica or you have back pain, then oftentimes this is the ultimate exam that you're going to get. So you're going to be looking for, and a radiologist is going to be looking for, areas of nerve impingement, places where the nerve is getting compressed. One of the things that's interesting about this is that, first of all, the way that we do these reports is by prose. Almost everything I do in radiology, I dictate. So I say, you know, so here's the report over here, right? This is what I dictate. And notice that's all prose. But with nerve impingement and this study, just like a lot of studies, but this one in particular, it really should be structured. So, for example, we grade nerve impingement by absent, present, and then mild, moderate, severe. And then it can only really happen on the right, on the left, in the center, and it happens at multiple levels. So really, it should be structured. But right now, we don't capture it that way. So we decided that this was an opportunity to do something that we've wanted to do for a long time, which is start really pushing the mandate around structured data, like actually getting the outputs of the model into structured data formats. So I'm going to play you an example. This is, over here on the left is Stuart, who's a neuroradiologist. This is our workstation at the center. And what I'm going to demonstrate for you is not just the model in action, but I'm going to show you integration and structured reporting. So as I mentioned, the PACS, our PACS system, like most PACS systems, don't have standard APIs. Some of them don't even have no way of interacting with them. So here, he just opened up the work list, and he's in the center here. Oh, sorry about that. Let's see if I can get this working. So he's going to open the work list. That's where all the patients are. He's going to open the study, clicking on the work list. Then over here, where his mouse is, he's now looking at the image. So he's got those two displays there in the center and on the right that show the images. Now he just clicked a button, which is our hack. It's essentially our way of grabbing the DICOM images, the medical images, and displaying them, but displaying them with the output from the machine learning algorithm. So those buttons on the bottom there, red, yellow, and red, that's right, medium, middle, and left, and like the level of stenosis. So he can go through the image, see if he agrees, he hits submit, and then he pushes it directly to the reporting environment. So that's the reporting environment where we usually do the dictation. And now he's going to go up the next level, and he's going to be looking for those areas of stenosis, trying to figure out whether he agrees with it. And if he agrees with it, he's going to hit submit, and there it populates over to the reporting environment. And he's going to do this through at 5 or 6 levels, and then he'll have his report. And what have you just accomplished here? Well, one, you've integrated this machine learning tool in the workflow. 2, you've incorporated structured data. And 3, you've probably made your radiologist faster and probably more reproducible. So it's one of those rare instances where you probably have pushed everything's kind of, you've pushed the boundary on multiple good fronts, right? So that took a fair bit of work to do the integration and all this stuff. All right, switching gears now a little bit. So this is a tool that is similar in sort of virtue as what we were talking about earlier with the longevity score that you get from a CT of the thorax. So we had 2 physicians come to us at the same time with 2 totally separate problems. One was I'm a thoracic surgeon, and I need to figure out what the likelihood of the patient doing well on the table is. And so I asked this thoracic surgeon, I said, how do you know that now? Like, how do you figure that out now? And he said, he kind of thought about it, and he's like, well, I guess if the patient can get themselves up on the table by themselves, they'll probably be okay. And I thought to myself, oh man, this is crazy that's the way that we're doing our functional testing. That's how we figure out whether people are going to make it through surgery? This is crazy. We have all this additional data, right? And everyone who's having a thorax surgery has one of these CTs. So first of all, I said, well, okay, we probably could figure out your general health. Probably from the CT, we can probably have there's probably a biomarker in there. At the same time, we were approached by someone who was interested in understanding how well someone would do on chemotherapy after a specific kind of cancer. And actually started to, this researcher felt that distribution, fat distribution relative to muscle, might actually be an early marker for someone recurring of a particular kind of cancer. And it turns out the same thing, you're trying to do the same thing, essentially just quantifying how much fat distribution, muscle versus bone. It's a really simple problem, but my goodness, it has a lot of potential benefit. And every time you get a CT scan, we're getting this data now, but we're not using it. We don't use it. We don't quantify that stuff now. So we ended up creating UNet, which essentially does this segmentation task, which it measures how much muscle you have versus visceral and extracorporeal fat that you have. Switching gears now a little bit more. So this is some work that's done in collaboration with the Martina Center. Turns out that you can figure out other things just by looking at features that right now radiologists kind of do one of these finger to the wind sort of things. When they look at this particular kind of a brain tumor, glioblastoma, the most common, also the most deadly kind of brain tumor. They'll look at it and they'll try to make a determine about its IDH status because that's important for prognosis. Also may change the way that you treat because we know that they look different, but we don't really quantify how. But Jay Cherie at the Martina Center is doing this task and actually created a classifier that is working pretty well. I also mentioned that Matt Rosen at the Martina Center is doing some work on image reconstruction. So why would you do this? Right now, what you do with an MRI, to create an MRI image, you get this thing called K-space, and you do the inverse Fourier transform on K-space, and you get the image. So the raw channel data is the K-space data there in the center. And there's multiple methods for doing the reconstruction. Much of the work in MRI over the last decade or so has been focused on ways to reduce the time of patient, time that you need or the amount of sampling that you need to create an image because patients move around, because they don't like spending very much time in the scanner because you have a lot of patients to go through, so really the focus has largely been there. And so the opportunity here is to use machine learning to do those reconstructions. This is AutoMap, which is Matt Rosen's work, doing the reconstruction on K-space, sparsely sampled. And you can see the reference image there, which is the inverse Fourier transform reconstruction, and AutoMap there in the center. Looks the same. And there's also some other kind of interesting benefits. Here's a standard reconstruction. And granted, this is a pretty extreme example. This is misaligned Cartesian Fourier that only really happens when you have kind of it's kind of like a hardware malfunction, more or less. But it's robust to all sorts of artifacts like these. So that's kind of an interesting finding. Okay, not just radiology though, right? So this is happening in multiple fields of medicine. This is some work that Kwanzang Li is doing. So this is a sentinel lymph node biopsy. So lymph node's been pulled out of a patient who had a breast lump taken out. And so what we're doing right now is sort of scanning through the image. All these purple dots are normal lymphocytes. But here in the bottom here is some pink. That's breast cancer. So you're going to see on the left here what the pathologist labeled. And on the right, you'll see the COVNET. So there's a high level of concordance. And you'll see that there are maybe a couple false positives with the COVNET, but really there's not. There's really what you're looking for is something that's sensitive. So pretty nice performance there. All right, so I can almost never get away with a talk without getting this question. So I figured I might as well just take it head on. What does this mean for radiologists? And what does it mean for pathologists? What does it mean for echocardiographers? So we start seeing these sorts of things, right? So MIT Tech Review, a new algorithm can spot pneumonia better than a radiologist. And then the next, I think it was in the next week, it was this: AI is continuing its assault on radiologists, and it felt like a war. And then, you know, and then we see these sorts of things like AI versus MD, and you guys know who this guy is, right? Jeff Hinton. All right. So it's just completely obvious that in 5 years, deep learning is going to do better than radiologists. He went on, it might be 10 years. I said this at a hospital. It did not go down too well. True that. That's not going to go down so well. So, you know, the reality is I've just showed that this technology works pretty well. And is this true? So what does this mean for radiologists or diagnosticians, or what does it mean for medicine, and what does it mean for maybe for all of us, right, at some level? I'll tell you that we've seen some pretty tremendous advancement in the field, and in practical terms, empirically, we've seen that deep learning and applied to radiology is effective. But there are some important caveats, which, you know, is a plus and a negative. So the plus is really that there's an opportunity to really advance the field. The negative is that really the faster we get this technology out, the better it's going to be for our patients. And the radiologists and pathologists and all the rest, there's a lot of work to do. So most of the radiologists that I work with are really excited to see this technology progress and are trying to adopt it as quickly as possible. But we have a challenge, and part of the challenge is validation. And some of the biggest challenges that I see right now, one is that the models do have heterogeneous performance depending on the training data. So the training data, depending on where it comes from, has either kind of geographic, demographic differences. But probably one of the biggest is the way that the images were acquired and the way that the data is ultimately labeled. So in the end, it's very hard to have standard heterogeneously labeled data acquired in the same way, and that introduces some real challenges. So that's number one. And then once you have those models, actually doing the testing and ensuring the safety of those models is the next big challenge. So it turns out to do the validation, you almost have to do all the things that you have to do to train a model, right? You need to have a tool which can do the annotations, right? Then you need an annotated data set to do the testing, right, in your clinical environment. So, you know, in that regard, we think to ourselves, if you have all those things and create the model yourself, and that's probably not the way. Ultimately, it's going to be some combination. We'll probably use pre-trained networks and then ultimately start training at the local sites to try to correct for local variance and scanner variance. But before we even get there, we need to start doing some of the testing and validation in the clinical environment. And here's one reason why. Was anyone done Kaggle competitions here? I'm sure a lot of you have. So might have done the Data Science Bowl in 2016 was lung cancer, pulmonary nodules. So not long after that, a lot of startups came out which said, you know, we have a screening tool for pulmonary nodules. Do you want to use it? And we thought to ourselves, yeah, of course. You know, if you have something that will work, let's try to get it into the workflow. And so to do this, we actually created a tool to annotate the data set and a test set. And then we ran multiple vendors through the system, and we tried to identify which ones were performing well and which ones didn't. And does anyone want to sort of guess what the outcome of that analysis was? Did they all work? Did none of them work? Or did some of them work? Does anyone want to guess? Huh? Huge variance, yeah, huge variance. So some performed beautifully in certain circumstances. Others performed terribly in all circumstances. And you know, the interesting thing about that is that a lot of them, because a lot of that came out of the Data Science Bowl, we had initially thought that we're essentially using the same data, so you're probably going to get relatively heterogeneous outcomes, right? But that's not true at all. So the reason the winners won is typically because they took that data and they gave it to some friends that knew how to do the annotations and that were willing to do them, and then sort of added additional value on top of the existing data set. So, so then the annotations themselves were quite heterogeneous. So, there are ways to get around this. You can ensemble the models, but then you're dealing with 5 or 10 different startups, right, all with their own models. So there's still some work that needs to be done here, and not all of it's technical. Some of it's kind of social. So that's one of the big challenges that we see in front of us, and that if you had to ask me what the biggest thing in the next year will be for us at the center, it's really this kind of stuff. It's like validating models coming through and making sure we can do that in a scalable way. Beyond that, we'll be expanding beyond diagnostics and things like that. But on that note, I'd like to say thank you and take any questions that you might have.
So listening to your talk, it sounded like you were expecting a future where at one point everything would converge on the right answer. If you use weather modeling as a metaphor, even today, when there's a big storm, you go online, you find 5, 10, 15 different models, and different earth scientists prefer different models.
Yeah.
There's an ensemble model, which is almost always not what happens. Don't you expect then that we'll have a heterogeneous environment in the future, and different clinicians will trust and proceed down different paths?
I think that's very likely. Yeah. So I think what's we're likely to see is that even without the heterogeneity that comes with demographic variation in your practice and differences in the scanners, the radiologists and the diagnosticians themselves have a lot of variance. And what they prefer and how they do the diagnosis themselves really be different. So I think this is going to be like a 3-step process, I hope. It's the first one will be the first set of models that come out that are trained on a big set of data, and they will universally be good, but not, a lot of them will be good, but not great. The next phase will be using those models as pre-trained networks and then you'll have local diagnosticians do additional training and hopefully try to get those models into a better position. But then the departments themselves will have a problem consuming that world, because now you've incorporated variance in a practice that's not supposed to have any variance. So then the third step will be converging all of that. I hope. That's my hope.
So in one of the projects you mentioned, you were trying to reconstruct images using sparse sampling. Mm-hmm. Can you brief us about what kind of models that you trained on? Were they trained on any prior clean data set before doing the reconstruction? Yeah, so that was work that Matt Rosen did, and I have to reach back in my brain. I'm not really sure. It's the AutoMap paper. It's in Nature, so I probably best to just take a look at the paper. Right.
What do you think about the whole explainability issue with AI? Because, to me, it seems like the biggest adoption problem would be that a pathologist or radiologist can explain kind of their findings, but it's harder for a machine learning model to do so. And so, how do you think this explainability problem can be solved?
I think the question is really about explainability within machine learning models, and essentially how do you drive adoption when someone doesn't know why the result is what it is, right? And so there's a couple ways to do that. We do use saliency maps when appropriate. In imaging, it's a little bit easier than in other fields, right? So saliency maps are already a good tool for problem solving. There's kind of like an infamous example that's floating around, which is there was a classifier, went to market, and then on one of the versions they implemented a saliency map, and the model was to look for pneumothorax, lung in the air in the lungs, between the lung and the chest wall, and the model was looking over the shoulder, and clearly was something weird was going on, and then we started to find failures. that multi-classifier models are another way to sort of get some explicability. But those are the two solutions that we have. And we're looking to all of you to help us solve this problem. Yeah.
So you talked a little bit about how these models, based on how the data is collected, become very sensitive to the input data. And small changes in machinery or whatever cause really bad performance. Are you guys working on anything that would allow the models to be less sensitive to their inputs and therefore generalize better across different departments and different machines, et cetera?
Yeah, I mean, if you treat the data as, or parts of the data as weakly labeled data, and you can incorporate some level of confidence metric with your training data, then that's one way to do it. I think there's not a really good solution yet, because we actually don't know how big the problem is. With a lot of segmentation tasks, actually the problem is not that big. So you need less data for a segmentation task, much less, oftentimes orders of magnitude less than a classification task, for example. So in those instances, all you do is you try to grab representative data from the place where the failure mode is coming from. But with classifiers, it's much harder, and it's hard to anticipate how it's going to fail too. So we don't know what the problem is. It's probably more on these classifiers than segmentation models. Yeah.
So it looks like you're doing a lot of stuff with like medical imaging. I'm curious if you could share your thoughts about machine learning for other types of medical data, like health record data, genetic data.
Yeah. So we started with imaging data for multiple reasons. One, came out of the Department of Radiology. Two, the data is relatively clean relative to other data sets and centralized. Three, last but not least, deep learning works really well on image data and video data, right? And maybe for some of the other things, the incremental value is less. So made a lot of sense to start there. I think where we're going is multimodality data. Some of our projects now are high-frequency data. So we deal with EEG data, data that's coming off monitors, things like ventilator data. So that's kind of the next phase here. With medical, with notes and things like the textual data, we actually had to start there because, as I mentioned, the very first problem is always cohort development. So that's always work in progress. And then finally, genomics. We actually don't touch genomics at this point. So we probably will once we start talking about multimodality data. We have some genomic markers that we use and things like the radiogenomics work that Jeshuri was doing. But a whole genome data we haven't really dealt with yet.
So have you experimented at all with experimental design? Like, you can come to the point you can have some confidence and suggest more scans, different scans. Anything like you're doing like that?
Yeah. I'm a little ashamed to say that most of this is still so early that we're trying to figure out which ways to walk. So most of it we kind of have normalized on the same sets of algorithms, probably like a lot of you. We typically start with a UNet. We don't do a whole lot in the in sort of titrating the algorithm is pretty straightforward, but it's not straightforward to figure out why the things are failing when they fail. And it's right now it's a lot of discovery because.
But you assume the data are those.
Yeah.
Or say we need.
Well, we don't even really make that assumption because as part of the discovery, we're getting other institution data from other geographies in the world. So we have data that's like coming in from different continents now. So it's a little bit of a black box for us. We're still kind of walking around in the dark. Capstone project.
Thanks for a great talk. I'm a clinician at the Brigham, and so low-hanging fruit is getting people to eat more fruit and walk more. How how do you see AI kind of working with behavioral economics to help us move forward in preventive healthcare?
Yeah, so that is a great question. So in our system, preventative care is a big deal, just like in most systems, right? But what we're talking about here is how do you start really pushing forward and sort of identifying, say, at-risk patients for early intervention, and how do you sort of move from where we are, which is largely looking at images and doing classification tasks, to actually identifying some of those at-risk patients and like feeding that data to people that can modify that risk. So you asked kind of, I think, about socioeconomic and like how do we motivate that way. I think it's still largely a technical question in some regards, because while there's awareness that we can use these models to identify risk, it's like an engineering and technical problem right now, because executing on operationalizing those models in our practice is really the biggest challenge. So it takes big investments in the healthcare systems to do that. We're doing what we can with things like, that I showed you the model where we're identifying fat distribution and things like that. That's very clearly something you can feed into a population risk model. And there's lots of other things that we're doing that's probably the same. But I think ultimately, once you've made those models, how do you get it into the hands of the people that can modify risk, like the nurses, the nurses that go out to the patient sites and things? That's the biggest gap that we have.
At the beginning, you talked about these new startups that are in the space, analytic and otherwise. Could you speak to a little bit of the relationship that's going on between these startups and institutions, and any recommendations you might have for those of us that might find ourselves in an entrepreneurial endeavor and might want to approach a provider to deliver the care?
Yeah, I mean, a really great question, because a lot of the stuff that's happening in this field is happening in the startup environment. And it's historically been very hard for startups to navigate the complexities of big AMCs, big academic medical centers. Before this gig, I was in a startup. So I feel your pain. So I think some AMCs have a good path for startups, and you kind of have to find that person, the people that have successfully integrated with startups. For example, at the Brigham, they've done a pretty good job of picking a couple great startups that they want to work with and actually incorporating them. And some hospitals just don't know how to do that. So the first thing is you got to find the right hospital, and then you got to find the pathway in. So I think that's number one. Number two is, a very common email I get is, hey, I'm from X startup. We're the best of the best. And we're in the next Google. And we can solve all your problems if you just give us all your data. And first of all, no, you can't. And second, there's no way that's ever going to happen, because the safety and governance of that data is really an important part of what we do, and it's important. So I'd say one of the things not to do is don't do that. Get yourself into a position where you've seen people who have incorporated startups within the practice before successfully. Don't go in with the presumption that you're going to solve all the problems, because you won't. Listen very carefully to them when they tell you what their problems are. That's probably that's probably product 101, but it's particularly problematic in healthcare. One more?
Can you say a little more about your model validation process?
Sure. So right now we go through the process of creating test sets, and we'll run them through a model, and typically we ask that model is either in Dockerized format or can be implemented on a VM easily enough or somewhere on the prem, on-prem. We'll run the test data through it, and then ultimately we'll run some statistics on it. That's our first pass, and oftentimes that's kind of where things fail. We will then pass a couple of examples of the most salient failure modes back to the people that made the model. If it works fine, which it hasn't gotten to that point yet, then we have mechanisms for implementing it in the workflow. The reality is we just haven't had that happen yet, unfortunately. Okay.
Thank you.
Thank you very much.